Your homework solutions for the problems I gave out on Thursday, October 9th, I guess, and are going to be due on Monday the 13th. At any rate, the homework sheet should be on Schoology. There's also a PDF of this on Schoology. By the way, this should say 200 meters. At any rate, let's go through and go through some of these examples. Remember my notes also on Schoology. So you have a submarine that's diving 110 meters at 10 degrees below the horizontal. It's basically split it up into its horizontal and vertical components. Opposite over hypotenuse is equal to sine of 10 degrees. Adjacent over hypotenuse is equal to cosine of 10 degrees. So you rearrange those to get the horizontal and vertical components, which are shown 19.1 meters down, 108.3 meters sideways. Again, make sure you're in degree mode. Number 2, you have 2 putts and you want to know the resultant. So 5.4 south, 6 east. I draw a vector diagram. Remember, that's tip to tail. And then the resultant is drawn from the beginning of the first vector to the end of the last vector. So if you have an east vector and a south vector, your resultant should be pointing to the southeast, not back to the northwest. At any rate, when I do that using Pythagorean theorem, get 8.07 meters. Angle is going to be inverse tan of 5.4 over 6. So that's 42 degrees. So this is 8.1 meters at 42 degrees south of east. Number 3, whenever I have something like this, I'm going to have to split each of these vectors into the horizontal and vertical components, just like I've done in an example in class, and just like we did for the vector bug lab when you were doing trigonometry. So for this, I chose south and west because it looks like it ends up south and west. But the initial one was going 100 meters east, so that's 0 south, negative 100 west. The second one, 300 south, 0 west. The third one, I'm redrawing down here, and that is 30 degrees south of west. So this part, opposite over hypotenuse, the southern part is going to be a sine function. The western part or component is going to be a cosine function. So I end up getting 150 sine of 30, 150 cosine of 30. Both those are positive because they're south and west. For number 4, we're going northwest. So again, I'm redrawing this last vector here and splitting it into components. So it's 60 degrees north of west. So the adjacent side of that is going to be west. The opposite side is going to be north. So the north is a sine function, the west is a cosine function. I'm not worried about the negatives down here, but I do put a negative up here in front of the math, just because if it's going north, that's negative south. It really doesn't matter which vertical or horizontal orientation you pick, but you need to be consistent with the math once you choose. So that becomes negative 173.2, positive 100. Now I've got overall, when I add these up, the southern components add up to 201.8 meters. The western components add up to 129.9 meters. I'm going to redraw this. You could either draw south first and then west, or west first and then south. Won't matter. When I do that, my resultant is 240 meters. My angle I get's around 33 degrees. That's 33 degrees west of south. Or, if you drew it the other way, you would have found out 57 degrees south of west. 4 is pretty simple. If you have 2 vectors going the same direction, you just simply add them up. That's 200 kilometers per hour. If they're going the opposite direction, you subtract them. That would have, in this case, have been 130 kilometers per hour to the right. For this one, you have 2 vectors acting concurrently with 15 newtons of force, 28 newtons of force, and it says there's 35 degrees in between them. So the tricky part about this is, to make a vector diagram, I've got to draw them tip to tail, even though they're acting at the same point. So one of the things I could do here, let's see if I can do this. Let's see what's going on here. Okay, that I don't know what's going on here. We're not going to draw that. There we go. So with this vector, if I start here, I'm showing a 15 to the east, and then I'm doing 28 newtons at 35 degrees north of east. It really doesn't matter. It just needs to be 35 degrees of different. So in this particular case, I just happen to draw one of these so it's on the axis, makes my life easier. You wouldn't, I mean, I prefer to avoid trig if I can. So for the first one, I've got 0 north, 15 east. The second one, I've got 28 times sine of 35 north. So that's 16.1 newtons. 28 times the cosine of 35 degrees east. That's 22.9 newtons. All I'm asking for here is the magnitude. And so, I think I screwed this up. I know I screwed this up. Okay, so you're seeing it in live action. So what I need to do here is I've got to add these up. And this is 16.1, but these two I've got to add together, so that's going to be 37.9. Down here, this is going to be 16.1 here. So my bet is it's going to be something different than the 28.0. Yep, I got 41.2. So I'm going to do this. I'm going to make that a little smaller. I'm going to make that where you can't see behind it. And this should be 41.2. I did not check my own work. So I think, yep, I screwed up. Okay. Well, see, you see it in live time. Okay. Anyhow, so that is fixed now. Make sure that the PDF is actually this one. But yeah, you see what I did there. Same principle, I just didn't add these up, which is annoying. Number 6 is a river problem. We did one of these in class for the most part. The end of the day Thursday, I had a couple of them which went online with my notes. So this is basically saying, hey, this person, the boat aims to get across the river as quickly as possible, and the boat can go 12 meters per second. The current is downstream at 3.5 meters per second. And then what's the velocity relative to an observer on shore? So if they're aiming east, going south, this is the resultant. So Pythagorean theorem gives us 12.5 meters per second, and inverse tangent of this gives us about 16 degrees downstream. So that's what an observer would see. If you want to figure out how much time it's going to take to cross the river, every 1 second, the boat would cross 12 meters. So in 2 seconds, it would cross 24 meters. In 10 seconds, it would cross 120 meters. So I have that total horizontal distance divided by the horizontal speed. I get around 113 seconds. You would not divide this by 12.5 because this distance is a horizontal distance. 12.5 is the velocity at an angle. There's other ways with similar triangles you could figure that out, but the simplest is if you have a horizontal distance and a horizontal component of speed, just use those. And then if you're in the water for 113 seconds, and each 1 second you're being pulled downstream by 3.5 meters per second, you would multiply those two together. And notice the units of seconds cancel out. You're left with meters, 397 meters downstream. So I showed you some equations here for this. You don't need to memorize those. We'll get to those at some point, but that's how you solve that. Problem 7, now you have someone and they want to cross and get across the river from where they start. So essentially they have to angle upstream, And I would draw that here where the person's aiming upstream at 9.5 meters per second, which is their swimming speed. Current's going down at 3.75 meters per second. So therefore, I can figure out that angle by using inverse sine. That's opposite over hypotenuse. Notice it's not opposite over adjacent because the person's got to angle upstream to end up directly across. So that's around 23 degrees upstream. And then the resultant, which is this dotted line, is where they're going to end up when they're fighting the current and trying to cross by going at this angle. The resultant would be that they would head 8.7 meters per second due east. Problem number 8 is another vector problem where it's basically three forces acting concurrently. So this is kind of similar to the one up here. I guess I probably didn't need to do both of those. So 60 newtons north, 35 newtons east, 40 newtons at 30 degrees east of south, and the resultant goes something like this. It looks northeast, so I picked north and east. 1 is 60 north, 0 east. 2 is 0 north, 35 east. This one I drew for number 3. And the southern component is the cosine of 30 degrees times 40. The eastern component is sine of 30 degrees times 40. And because I chose north up here, the southern part would be negative. So I'm going to have 60 minus 34.6, and then 35 plus 20. Again, this is the unrounded part. I don't really care where you round. And I end up getting a resultant of 60.6 newtons, 25 degrees north of east. The equilibriant is exactly the same force, exactly the opposite direction. So if I said 25 degrees north of east, this is 25 degrees south of west. And for problem number 9, if you want me to go over it, I will do that in class, and I will include that in the scan, but I'm not going to talk about that right here, because that's just another example where it's just a little, kind of very similar to number 8 and number 3. Thanks.